One of the most infamous things in calculus is the derivative. And I know it might seem weird that I'm releasing my derivatives video before I release my second limits video, but trust me, by the end of this you'll understand why. One thing that we can do to make sense of derivatives and what they actually are is to go back to the y equals mx plus b days and graph a simple linear function. One of the most important things to consider about a linear function such as this is the m value, or the slope, the steepness of the line. And we always do this by finding the change in y over the change in x. But what if I wanted to find the slope of something that wasn't linear? Like I was trying to find the speed of a car whose distance was a nonlinear function. Let's say x squared. This would be much harder, and it's clear that there's something different that must happen. One way to visualize slope on a nonlinear function is with secant lines. Secant lines are pretty much the average rate of change between 2 points, because I am sketching a line that goes through 2 points on the quadratic graph. And if I were to take the slope of that, it would be the average slope between the 2 points. This is a good way of approximating slope at a point if I choose 2 points that are near it and calculate the average rate of change, and it works to an extent. If I remove the secant line from the graph, I can show you something pretty cool that the pioneers of calculus noticed about curves. As you can see, when we zoom in incredibly close onto a curved line, it seems to approximate a straight line. And mathematicians, we know how to take the slope of a straight line. As I said before, it's just the change in y over the change in x. So what they were thinking is that, what if I made a slope formula, but for a very, very small distance, taking the change in y and the change in x and shrinking them down to a scale where the curve would become a straight line. If I bring back the secant line on the graph, it will help to visualize what I was saying before about the x values and y values getting smaller and smaller. So here I have 2 points on the graph and a line drawn through them. The first point is x, and the second point is a certain distance h away from it. So therefore, the y values of the points are going to be f of x and f of x plus h, because I am moving the x value h units to the right, therefore adding h to x. Now, if I wanted to decrease these distances, I would make h go as close to 0 as possible, so that I can approximate the slope at this quote-unquote straight line. Let's see what happens when I do that. As you can see, as h gets closer and closer to being 0, these points get closer and closer to being on top of each other, to the point where it looks like we're taking the slope of this graph at a singular point. And this is exactly what we're looking for. We want this graph to be as close to a straight line as possible by essentially zooming in infinitely with points. Using our knowledge of both calculus and how the slope of a line works, we can begin to form an expression for what the slope of a graph will be at a singular point. Since we're decreasing the distance between the x values, we're going for a limit as the distance h goes to 0. And obviously, slope is in the form of the change in y over the change in x. If you recall the graph, our two y values were f of x plus h and f of x. The difference between these 2 points is going to be our difference in y. So the top of the expression is f of x plus h minus f of x. And our two x values in the graph were x and x plus h, because it moved a certain distance h over. And our difference in x will be the difference between these 2 points, x plus h minus x. Now you may notice that there's a little bit of canceling here, and we can get a more simplified expression as just limit as h approaches 0 of f of x plus h minus f of x over h. And this is one of the most powerful formulas in all of mathematics, as it allows you to get the slope of a tangent line at that point. There's one more formula that I would like to talk about that is very similar to the formula that we were just looking at, and it is the formula to actually just directly find the slope of a tangent line at a certain point, rather than finding a function that would give you the slope of the tangent line at any point. And this one is very similar because it is formatted as limit as x approaches a of f of x minus f of a over x minus a. And again, this makes sense because our y value would be f of x and f of a, and our x values would be x and a. So we just want to make sure that x is getting as close to a as possible, and we want to make sure that f of x is getting as close to f of a as possible, and that's why we're taking a limit as x goes to a, and then doing our regular slope formula of the difference in y over the difference in x. And this is just another formula that you might see. The last thing I want to do before finishing off this video is just going through an example of what it's like to use one of these formulas to actually calculate the derivative of a function. So here I have the first principles of x squared, where x squared is my f of x. So I have the limit as h approaches 0 of x plus h squared minus x squared over h, because I plugged in x squared for f of x. Now I'm going to just go ahead and expand that x plus h squared into x squared plus 2xh plus h squared. As you'll notice, the x squareds in the numerator will cancel out, and I will end up with 2xh plus h squared over h. And now I can factor an h out of both of the terms in the numerator to get h times 2x plus h. And now I can go ahead and cancel the h's and just end up with the limit as h approaches 0 of 2x plus h. But if you'll remember from my limits video, if we take the limit out of indeterminate form, we can go ahead and use direct substitution, and we end up with 2x plus 0, which is just 2x. Therefore, the derivative of x squared is 2x, so at any point x, the slope of the tangent line will just be 2 times that number. And this is commonly denoted as dy over dx of f of x, or you'll also sometimes see f prime of x. And the number of primes denotes the number of derivatives you're taking, so f prime prime of x would be the second derivative of f of x, f prime prime prime, so on and so forth. And the power on the d and the x in d over dx is also the number of derivatives. So d squared over dx squared of f of x would be the second derivative of x, so on and so forth. Overall, I hope you enjoyed this video and found it an easy way to sort of understand the core of what derivatives really are, where they come from, how to use the formulas, and just in general where they come from again. I've left some questions up on the screen that you can try. If you have any questions, leave a comment. And in the next derivatives video, I'm probably going to yap about continuity again, so I hope you tune in for that. Bye.